So, good morning. I will be talking about a computationally universal phase of quantum matter, and maybe somewhat along the way tell you what this is. Yeah. So now let's start with this. So this is a stylized phase diagram of water. Laser? Yeah. Okay. So here you have the temperature. Oh. Not here. Here you have the temperature axis, and here you have the pressure axis, so low pressure, high pressure, low temperature, high temperature. This is all liquid water, and we have a complex property of this phase of water that resides pretty much everywhere in the entire phase diagram, and that's life. Yeah? You find life at near boiling temperature, at ultra-high pressures. You find it at ultra-high pressures and low temperature, pretty much everywhere in the phase diagram. Somewhere in that phase diagram you find us. Okay, so it's a complex property existing in the entire phase. It's a property of the phase. Okay, so that's not the property we will be talking about, though. So the property we will be talking about is quantum computation. So we are relating phases of matter, and I will tell you in a moment what the ingredients are, to quantum computation. When do phases of matter support quantum computation? And in particular, when do phases of matter support universal quantum computation? So this is what I'll be talking about. Yeah, and so my ingredients are symmetry, it's very important. We will be talking about zero temperature, so we'll be talking about ground states of Hamiltonians, and we will be talking about spin lattices. So maybe at this point, let me try to make a connection to the first talk that we heard this morning. So there, the subject of study was topological order. Here we are talking about physical order, just like that, but it's a different physical order we are talking about, namely symmetry-protected topological order. So we will be taking symmetry-protected topologically ordered phases and investigate their usefulness for quantum computation. Okay? Good. So now I think I can also make the comment about quantum information theory, because I think by now you know that this talk is going to be about quantum computation. So what's my link to quantum information theory? Well, yeah, I thought about that a little bit, and what I came up with is Rolf Landauer. Yeah, Rolf Landauer's famous statement, information is physical. So irrespective of how you think about the question, what I'm going to tell you about, you can use to make up your mind, maybe revise your opinion, or verify your opinion. Good. So let's get started. So how are we going to use a phase of matter for quantum computation? Or more precisely, how are we going to use states in a phase for quantum computation? And so they will be utilized by measurement-based quantum computation. So I will explain this later. So the process of computation is driven by measurements on a given quantum states, and these states now come from these symmetry-protected phases. Yeah? So this is how the states come in. So it is known that there is states out there that support universal quantum computation. So the 2D cluster state would be one example. It was the original example. By now, many more examples are known. And what this talk is about is there is an entire phase surrounding the cluster state that is also computationally universal. So any state in that phase has the same universal power for quantum computation. Good. So let me summarize before we begin what we consider. So yeah, as I already said this, but let me summarize on one slide. So we look for unique phases with unique ground states of certain spin Hamiltonians. All of this happens in the presence of symmetry, so the Hamiltonian is invariant under a certain symmetry, and I will specify these symmetries later. And we talk about spins in spatial dimension 2. So this is grids, and you will also learn later why this is so. why one-dimensional systems are not sufficient. And for this system, we show that there exists a phase of quantum matter that is universal for quantum computation. So computational power is uniform. You pick a state as a resource state from that phase, and whatever state you pick, the computational power that it provides is the same. Okay, good. So after so much talking, maybe it's time for an outline. So I'll give you a little bit of a background. So I will review measurement-based quantum computation for you if you haven't heard about it, although you will probably won't learn it here. It would be a talk by itself. Okay, and so then I tell you a little bit about computational phases of quantum matter. I will give you two motivations and a short history of the question. So the subject is by now 12, 13 years old. Yeah, and I want to tell you a little bit about how the field shaped. And then I come to the central part of my talk. I'll sketch out what this phase of matter looks like. So let's get started. Okay, part one is a review of measurement-based quantum computation. So you all know that there is two types of processes in quantum mechanics that are very different from one another. So you have unitary evolution, you have measurement, and you can build quantum computation on both. If you build quantum computation on unitaries, you get the circuit model. If you build quantum computation on measurement, then you get measurement-based quantum computation. And it works as follows. So you begin with some entangled state of a suitable kind. Not every entangled state will do. We'll get to that later also. And then you begin to measure. You measure every particle in that state. And when you do a measurement, you cannot choose the outcome. That's going to be random, and you'll have to live with what you get. But you can choose the measurement basis. And so your resource state is like a blank sheet of paper. And by the choice of the measurement bases, you can imprint a quantum algorithm on that substrate. So information is written onto that resource, processed, and read out by the measurements alone. Yeah? And so it now happens that there are some universal states, so some resource states that allow for universal quantum computation in this scheme. So there's the cluster state, the AKLT state, but how broad this set of states is, how many there are, how many different types of states there are, this is pretty much unknown, even now. Okay, and so that's also our question. We would like to have a theory of resource states, but we are far from being there. Okay, so that was measurement-based quantum computation. For those who do not know it, I hope you got a general idea of what this is. Good, so let's now continue with the second part. So this is the history of the field, and before the history of the field, a bit of a motivation. So I give you two motivations. The first is a fairly general motivation. So, I take the night sky here as a kind of counterpart of Hilbert space. And so we could ask, okay, so how are resources, states for measurement-based quantum computation distributed in Hilbert space? Are they kind of individual points separated from another, or are they more, do they form a continuous object like what the Milky Way appears to be from far away? Yeah, so this is a question that we are interested in, and very little is known. So the examples that were previously described, I mean, they are like individual stars and little in between. So here's a general result. This is one of the few general results we have. So resource states in measurement-based quantum computation are rare in Hilbert space. Namely, if you go by volume, it's only the tiniest fraction of states that can potentially be computationally useful for anything. Yeah, they're doing better than flipping a coin. And the reason for that is rather interesting. Namely, all the other states are too entangled to be useful. So entanglement isn't always helping you. All right, and now that we know that, we may ask ourselves, what about symmetry? Does symmetry change that picture? Now we are getting back to the slide that I showed you at the beginning. Now we do indeed find a change. Now we see that the parameter space, it separates into these phases, and computational power is uniform across these phases. It can still be little power, some power, universal power, but whatever it is uniform across phases, so the statement of resource states being rare changes a bit. Okay, and we want to make that point and explore it. Good. Second motivation, maybe more particle physics inspired. By the way, this picture, for now it's just a pretty picture. I will explain it later. Let's focus on the questions here. So this is a particle physics perhaps inspired question, and it is, can schemes of measurement-based quantum computation be classified by symmetry? Say, like particles in particle physics can be. Yeah, so this is a question that we may ask ourselves. Suppose we had a positive answer to this question. Then does it have any bearing on quantum algorithms? Can we classify quantum algorithms by symmetry? Maybe. So, as I will tell you, we know a lot about the first question. We know next to nothing about the second question. Good. So these are the motivations. Let me now continue with the history of the subject. So this has two beginnings, one with Stephen Bartlett, one with Akimasa Miyake, and let me explain to you what Miyake did. So Miyake considered a scheme of quantum computation that was half measurement-based, half adiabatic. So he was looking at the ground state of some spin chain, and the respectively last spin in that chain would be decoupled by lowering down the coupling to the next neighbor in the chain, and once it was decoupled, the particle would be measured, like in measurement-based quantum computation. And that gave you, a proper scheme of quantum computation. And what was interesting about it was that it relied only on the presence of symmetry. You didn't need to know what the Hamiltonian was, you didn't need to know what the ground state was. All you needed to know was the symmetry. And he realized on the spot that this was connected to symmetry-protected topological order. So this is the beginning of this field, I would say. So, yeah. All right. Next paper that I would like to review is simultaneously a step forward and a step backward. So the step forward is that it's now measurement-based quantum computation proper. There is no adiabatic component in it anymore. But the step backward is that it is only about transmission of information, not computation. So what Doherty and Bartlett and company showed was that you can shuttle a quantum state through a spin chain in a teleportation-like protocol, namely measurement-based quantum computation, and that works in an entire symmetry-protected phase, anywhere in that phase. Why this paper remained relevant today, or till today, is that they imported the mathematical framework for how to deal with these situations. That framework is of group cohomology. It was already known among the condensed matter physicists, and these guys imported it to quantum computation. And yeah, you find this went into the genetic material of this whole subject. So people use that framework to this day. So that's why this paper is important. Okay, back to Miyake. So he improved both on what I just showed you and his first paper that I presented. So this is now a computationally universal phase in one dimension. So this is measurement-based quantum computation proper, no adiabatic component. This is how he improves upon his earlier paper, and it is computation, not just shuttling of information. So this is how he improves about Bartlett et al. Oh, everything okay? Yeah, good? Okay, good then. Yeah, so this is the, the term computational phase of matter was coined 5 years earlier than this. But this was the first proof that such a thing exists. Now I come to explain to you this picture that I showed you before. This is the SPT to MBQC meat grinder, and it is very closely related to Miyake's paper that I just showed you, but it points out that this phenomenon of computational phases of matter is everywhere. It's not just this one particular phase that Miyake constructed. And in fact, what was shown here is this SPT to MBQC meat grinder. So what you grind is the mathematical structure that defines SPT phases, namely the symmetry group and this cohomological thing. I don't explain it to you, that describes the phase. You put it in, crank this, so this is an algorithm, and out comes a scheme of measurement-based quantum computation. And it tells you which group of unitaries you can implement and which observables, which logical observables you can measure. Yeah, and so this is, I mean, on an earlier motivation slide, we talked about classification as a goal. We have this here. So this is the data from the classification of phases. You crank it in, and you get the MBQC schemes. Only grain of salt that you have to take it with is that this holds for 1D only. It's only a one-dimensional result, and as we see shortly, one dimension isn't so interesting. At this point, I must ask, how much time have I left? Bit more than 5 minutes. Oh, I need to speak faster then. Good. Okay, so let's look at what we have seen before. All of this was in one dimension, one spatial dimension, and phenomenology-wise, that isn't so interesting. And the reason is the following. When you map measurement-based quantum computation to the circuit model, which you can do, then you lose one dimension. So if you start with one dimension, you go to 0 dimensions, and this means fixed number of logical qubits. That does not give you universality. So you need to start in higher dimension, 2 or above. Okay, so if you want to have universality, we need to go to 2 dimensions, and that's what we do. Yeah, okay, so let's talk about whether you can have such a thing. And indeed you can. So let me explain to you what our result is in that regard, and then just let me throw at you the basic proof technique without explaining much. But that's, I think, what I can do in my remaining time. So we are looking at a torus, so a spin lattice embedded on a torus, and this is just out of laziness because periodic boundary conditions is the easiest for us to handle. And this is what the symmetries look like. So they are not, they are not gauge symmetries, they are not local, but they act differently on different sites in the lattice. So this is called subsystem symmetries. And here you see it, You have non-trivial action along these diagonal lines, like so, and then you also have all these translates. When you examine the 2D cluster state, you find that it satisfies these symmetries. So this is in the cluster state stabilizer. And so the phase that we are looking at is the phase with the symmetries and which has the cluster state in it. And we can show that for this entire phase, all ground states except maybe set of measure 0 are universal resources for measurement-based quantum computation. Okay, how do we show this? Just as an outline, we use the tensor network language. So you have your very familiar tensors in the Munich area. So the red lines represent the physical legs, black lines virtual legs. So these are contracted over, and those represent physical systems. Okay, so the object to discuss now is such an individual tensor. And we can show that every state in our phase of interest can be described by tensors that have a certain set of symmetries, a certain group of symmetries, like so. And in fact, if you add one more tensor symmetry to that group, or one more generator, then you get one unique solution, and that's the cluster state. But we don't do that. If we don't do that, we get the entire phase. So this holds in the entire phase. Okay, final point. How does this relate to computation? You get computation out of symmetry Lego. Now It's almost like a game, yeah? You're putting these symmetries together in such a way that the symmetries match across the virtual links. And then you can reason about quantum logic. So this is the simplest case. It's just the identity gate. What we have here in our tensor network is our virtual quantum register, and these are observables acting on this quantum register, okay? And so we see that in a rather complicated song and dance, a local Z operator maps to itself, a local X operator maps to itself, and we have all the translates also. So this gives you the identity. Huh? You have to work for the identity a little bit in this scheme. You can also do a universal set of gates. Again, I'm just sketching it out. Here is how you would represent an entangling gate. So it's again explained in quotes, by a symmetry that we previously had. And yeah, so you can get that gate here by measuring a particular qubit in a symmetry breaking basis in a certain fashion, and you get other gates, and together they form a universal set. So this is how you get that. I think it's time for me to conclude. So let me just say, let me summarize what we achieved, and also let me tell you a little bit about the work that's currently going on in my group in this regard. So we had previously achieved a classification in one dimension, at least for certain symmetry groups. And in 2D, we have no classification but examples. We presented a first example of a computational universal phase, and by now people know quite a few more of these phases. But they are essentially cluster state-like on various lattices. Good, so what are my students doing? So here's Paul Herringer. So he is now moving towards the classification aspect of this. He's looking at different tensors with different symmetries. And the question is, what kind of computation do they give you? Can you classify that? And Arnab, who is in the audience here, thinks about long-range correlations. Yeah? So symmetry-protected topologically ordered phases are short-range entangled, but if you go very near the phase boundary, then you form long-range correlations, and the question is, how do they affect the computation? Good. So now let me summarize. So we have found a computationally universal phase in SPT ordered systems. So that's the problem we have solved. The classification question is completely open. And final advertisement, Symmetry Lego is fun. Try it. Thank you.
All right. Thank you very much for the very interesting talk. Are there any questions? So, okay, let me start with the question then. So, for all the states in this, in this symmetry-protected phase, would even the circus be exactly the same, or do you still need to do some adaptations in your gates to account for the different states which are in this phase?
Oh, thank you very much. It's a very good question. There will be differences, minor differences. So all the adaptation business is also uniform. So we know in measurement-based quantum computation, I didn't talk about it, that measurement bases need to be adjusted according to previously obtained measurement outcomes, and that's completely the same. However, there is a difference. So when I measure in a certain basis of the symmetry-respecting basis, only then am I implementing gates. And how does the measurement basis convert into the gate implemented? That is now a matter of where you are in the phase. That is something you need to know.
Okay, thank you. Other questions? Well, your talk was extremely clear. So if not, let's thank the speaker again.